Hi everyone, it's me, Dr. V, and again, it's a good day to do some AP Chemistry exam review. In this webcast, I'd like to talk through free response question number 4 from the 2024 exam. Now, in case you weren't aware of it already, there are some changes coming for the 2025 exam. This year's exam will be a hybrid exam, and that means the multiple choice questions will be administered and taken completely online. You'll be doing that in the Blue Book app. And if you haven't done your Blue Book test runs yet, you should definitely do that. The free response questions will be presented to you online, also in the Blue Book app. But you're going to write your answers on paper in a paper answer book, and any diagrams that you need to interact with will be included in your answer book. Some other logistics, just to be aware of them, is that you will have a paper periodic table for the entire test, and you'll have scratch paper that you can use for the multiple choice questions. For the entire exam, however, the reference sheet, that formula sheet, will only be available digitally. You'll have to pull it down in Blue Book anytime you need to look up any equations. Also, throughout the entire exam, you'll have access to the online Desmos graphing calculator, and if you're familiar with that, it's super easy to use. You'll also have the option for an approved handheld calculator throughout the entire exam. So you're going to use whichever makes more sense for you, whatever's more comfortable for you. In terms of this webcast, we are working through 2024 free response question number 4. And this is one of the 4 short free response questions in any AP Chemistry exam. That means it's scored out of 4 points. And these short free response questions typically have 3 or 4 parts to them. It can vary a little bit. Before we go any further, grab your calculator, your periodic table, your formula sheet, some paper to write down your work. Because what I want you to do is listen to me introduce each part of the problem and then try to answer it on your own before you listen to my explanation. My total purpose here is to help you write better answers for the exam so you can demonstrate what you know about chemistry, right? That's the whole goal of this. I also want you to keep track of your work as you go and keep track of your score. Did you earn the point for that part or not? How do you need to enhance your answer? What did you not remember? Again, it's all with the goal of you being able to demonstrate your knowledge in this exam setting. So let's jump right into the problem. A student performs an experiment to determine the specific heat capacity of a metal. Okay, this is going to be a calorimetry problem. I can see that already. The student places a cube of the metal in boiling water, so its temperature will be 100.0 degrees Celsius. The student then places the metal cube into a calorimeter that contains water and records the highest temperature of the water. A data table and a diagram of the thermometer at the highest temperature are shown. So we know the mass of the metal cube, we know the mass of the water, we know the initial temperature of the metal cube and the initial temperature of the water, and we have the highest temperature of the water, and then we have this picture of a styrofoam cup calorimeter and an enlarged picture of the thermometer. Part A asks, what should the student report as the highest temperature of the water? So we want to know, do you know how to report data correctly? That's what this question is really about. When you look at the thermometer, you should notice right away that A, you have to read upwards. 30 is below 40, but also it's marked to 1 degree intervals. And since it's marked to the ones place, you need to add 1 estimated digit. So you're going to report the last digit of your answer, that estimated digit, in the 10th place. It looks like the bar is halfway between 38 and 39. So I thought that the best reading for this was 38.5 degrees Celsius. There's probably a little bit of wiggle room in the value of that last digit. It is estimated. If you had written down 38.4 or 38.6, you're fine. Farther away than that, you're pushing it a little bit. But that's what you needed to record for 1 point for part A. Part B continues, a particle level representation of water molecules in the calorimeter before and after the metal cube was added is shown. And here we go, this is before. The length of the arrows in the before diagram represents the speed of the water molecules in the system. In the after diagram, draw an arrow for each molecule to indicate how the speed of the molecules changes after the metal cube is added. Well, we know that the water temperature went up, and that means because the water temperature went up, the average speed of the water molecules will increase. And therefore, since the molecules are going faster, the arrows that I draw on average need to be longer than the arrows in the before diagram. So that's what I drew. With my rainbow pen, everything's better with the rainbow pen. Notice that they're longer. It doesn't really matter what direction they're pointing in. On average, the arrows are longer. They don't all have to be the same length. They just need to be longer on average than the before arrows. That's what you needed to have in your answer for part B to earn the point. Assuming the metal transfers 2,940 joules of thermal energy to the water, calculate the specific heat of the metal in joules per grams per degree Celsius. This is a calorimetry problem, Q equals mc delta T. And we are solving for C. If we go back and look at our data table, we know the mass of the metal cube, we know the mass of the water, we knew the initial temperature of the metal cube and the initial temperature of the water, and we of course had measured the highest temperature of the water in our answer to part A. So let's think about what we need to substitute in here. First, I want to rearrange my Q equals mc delta T calculation to solve for C. It's Q over m times delta T in the denominator there. And if we read through the question and what's going on, I'm transferring 2,940 joules of thermal energy to the water. So the heat loss, I can think of this as having a negative sign, right? The energy is going out of the metal, so negative 2,940 joules. So that's Q. Now I know the mass of the metal cube. I'm doing this calculation in terms of the metal. This is not about the water. This is about the metal. And the mass of the metal cube was 98.1 grams. So that's my M value for this problem. I also have to find delta T. Now, delta T is defined as T final minus T initial, right? We always do final minus initial. And we knew the initial temperature of the water was 100.0 degrees Celsius. And we measured the highest temperature of the water as 38.5 degrees Celsius. So we can calculate the value for delta T for the metal as 38.5 minus 100.0 degrees Celsius, or minus 61.5 degrees Celsius. We do want to be consistent with our signs here, since we're working with the metal and the metal's losing energy. So we can substitute these values into our expression. Negative 2,940 joules divided by the mass of 98.1, and which is also multiplied by the delta T of minus 61.5 degrees Celsius. Of course, those negative signs cancel out. I am going to get a positive value for the specific heat of the metal, which does make sense. So I get a specific heat of 0.487 joules per grams per degree Celsius. I needed to show this work and set up to earn 1 point. Make sure you have the work, okay? Always show your work. In a second experiment, 2,940 joules of thermal energy is transferred from 98.1 grams of aluminum, which has a specific heat capacity of 0.897 joules per grams per degree Celsius. Explain how the magnitude of the temperature change of the aluminum compares with the magnitude of the temperature change of the metal in the original experiment. So let's think through this. Delta T for the experiment, for this new experiment, has to be smaller than delta T for the first experiment. Why? We know it's a Q equals mc delta T problem. Q is the same for both experiments. The mass of the metal is the same for both experiments, right? In experiment 1, the specific heat was 0.487 joules per grams per degree Celsius. And now the specific heat is 0.897 joules per grams per degree Celsius. So the value of the specific heat has gone up, which means delta T has to go down in order for, because Q and M are the same. So if C increases with Q and M constant, the temperature change has to decrease for the aluminum experiment compared to the first experiment. Now, another way to approach part D would be literally to calculate delta T. So the delta T for aluminum would be the Q for aluminum divided by the mass divided by its specific heat. And if we substitute those all in, we get a delta T of 33.4 degrees Celsius. And that's definitely a smaller magnitude of change than the 61.5 degree change we saw in the original experiment. So we actually had two ways that we could have chosen to answer part D. We do need to make a claim that's correct and back it up appropriately to earn the point. How did you do? So the average score in question 4 in 2024 was 2.60 points out of 4, which is pretty good. So if you earned 2 points or 3 points, you're right on track. If you earned all 4 points, kudos to you. You're doing well. You've got a good grasp on calorimetry. Always a good set of skills to make sure you can do. Make sure you know how to work with Q equals mc delta T. Pay really close attention to what part of the system you're interacting with, which part is losing energy, what part is gaining energy, all those kinds of things. If you found this helpful, like the video and leave a comment, and remember to subscribe to my channel so you get all my latest updates. Have a great day and keep studying chemistry.